You welcome to Moto Online YouTube channel that is basically helping students to improve on their academic performance. We are here to spice up on what you already know, and equally we introduce on what you don't know, such that you can simplify this new interesting competence-based curriculum. Today, I'm going to take you through a physics scenario about modern physics. Before I go any further, I'm teacher Noah Mogulumiza, a physics educator. Now, in this video, we shall look at a scenario in modern physics, how they are set and how we can possibly respond to them. A scenario at hand, we have the government has discovered a precious and rare mineral in a certain part of the country. A team of men picked samples and kept them in a store of one of the hospitals where photographic plates are also stored. The mineral was checked on regularly and they made the following observations. The first observation, all photographic plates had darkened. Another observation, its mass reduced spontaneously with time as shown below. So we have the table showing the spontaneous disintegration of this rare mineral. So this is the table. It has the mass and then the time. So initially, when the time was 0, it was measuring 200 grams. Then as time went on, equally the mass spontaneously reduced. Now, as a physics learner, we have the following tasks. 1, support the view that the mineral is radioactive. So they want us to give proof whether this mineral is radioactive or not. There is that view or proposal that that mineral was probably radioactive. Part B, use the graph to estimate its half-life. We again have another term, half-life. And then part C, explain the best way of storing this rare mineral. Then lastly, what are the dangers of exposing this mineral to the public? Now, to begin with, this mineral, after these men extracted it and they stored it in a safe place in a hospital where photographic plates were also kept. We all know the use of photographic plates. Now, when they stored this mineral, rare mineral, for them they didn't know that it was radioactive, but to their surprise, they found the photographic plates had darkened. That was as if not enough. Even the mass had reduced. It was 200, but after 30 days, they only found 25 grams. This now made them to propose that this mineral, rare mineral, might be radioactive. So they want you as a physics learner to support the view that the mineral was radioactive. First of all, you have to know what a radioactive item is. Radioactive comes from radioactivity. Radioactivity, by definition, it is the spontaneous or continuous disintegration of a heavy unstable nucleus to form a stable nucleus accompanied by the release of energy. The spontaneous disintegration of a heavy unstable nucleus to form a stable nucleus accompanied by the release of energy and radiations. Now, the fact that this mineral was initially 200 grams, and then, to their surprise, after some period of time, they found that it had reduced spontaneously or continuously. that automatically means that this material was radioactive. Now, the photographic plates being darkened, it simply means that there was emission or production of of uh, of radiations. Radiations, we are meaning, can be gamma rays, can be they can be alpha particles, or they can be beta particles. There are actually three. They can be beta, alpha, or gamma. It is those particles that made the photographic plate to get darkened. Then this mineral was radioactive. So our response to this, one, you first need to describe or to give a brief explanation on a radioactive mineral or item. So a radioactive sample is that sample that spontaneously or continuously disintegrates to form a stable one with emission or with the release of energy. Then on part B, they want us to use a graph to estimate the half-life of that rare mineral. For the fact that this mineral was radioactive, because it darkened the photographic plates, that means there was emission of radiations. The radiation is, in this case, we are meaning alpha particles. Alpha particles are written, emission of alpha particles, and these are written like that, alpha particles. Then we have also the beta particles or beta radiations, beta, and then we have the gamma radiations. The gamma radiations that are represented by a symbol gamma. Now, it is these radiations or particles that made the photographic plate to get darkened. And the truth is that rare mineral was radioactive because it spontaneously disintegrated and it released different particles like a gamma, beta, and the alpha that made the photographic plate to get darkened. In part B, they want us to use a graph to estimate half-life. Now, before we find half-life using our graph, which is denoted as T a half, time a half, we need to first know what half-life means. Half-life simply means the time taken for a radioactive sample to decay half its original mass. The time taken for a radioactive sample to decay half its original mass. Now, case in a point, this mineral here, the original mass of it was 200. Now, the time that mineral took to decay half its original mass, when you half 200 grams, you get 100 grams. Now, the time it takes this mineral to decay to 100 grams or to become now 100 grams, it is what we refer to as half-life. It is denoted by T a half, as you can see here. So half-life is the time taken for a radioactive mineral or for a radioactive sample to decay half its original mass. The fact that we've already proved that this rare mineral was radioactive in part A, there is no doubt that now it was radioactive. So it's now a matter of us finding the half-life using graph. We have quite a number of methods that we can use to find the half-life, among which we have the formula, the crude method, and then the graphical. But this question is specific on one method, and that is none other than the graphical method. So we shall also look otherwise not other than using the graphical method. Now, we have a graph here. We are going to plot a graph of mass against time, but this time is in days. So, when you look at the initial mass was 200. So before this mineral was disintegrated to release some particles, the alpha, gamma, and beta, its original mass was 200 when time was 0 days. So that means I can now start plotting. But before you plot, you have to get a scale that can accommodate all the data given. Get a suitable scale that can accommodate all your data and be able to appropriately use that scale. For me, I'm just going to use my square board here, and I plot such that I can try to get the half-life of that rare mineral. So when time is 0 on this time axis or x-axis, then this axis here, you can call it y-axis, and in this case, it is now the mass axis, which is now representing the mass. So it is mass against the time, but time is in days. So when time was 0, the mass was original, which is now 200. So my 200 is here. I can mark there. So when time is 0, mass was 100. Now we go. When time moved on, when time was now 4 days, my 4 days are around here. The mass reduced spontaneously, continuously. Spontaneous, this word spontaneous simply means continuous. There is continuous reduction in the mass. You can see that it was 200, but now it is 25. So it just continuously reduced the mass as time goes on. So when time was 4 days, it was found out that now the mass was 150 grams. So this is, if this from here to here is 20, that means the interval is 10-10. So if I want to get 150, already I have 140 here, and the interval is 10-10. So that means here it is 150. My 4 is here, so 4 tallies with 150. So 150 is here. I put a mark there. Then also plot 16 and 70. So when time was 16 days are around here. The mass that at that moment was 70. So this is the 60, then 70 grams around here. So it is now 16 against 70. So around here. But for you, when you have a square paper or a graph paper, you get something clear, actually even more clear than mine. When time was 28 days, the mass at that moment had reduced to 35 grams. So when time is 28, so 28 is around here, and then it goes with the 35. But this is 40, 50. So this is 20, 30, 35 is around here. So it is 28 against 35. So against 35 around here. Around here. Then finally, when time was 30 days, the mass at that moment, mass that had remained was 25 grams. So 30 was 20, goes with 25. So this is 20, then 25 is around here. Now, after you plotting, we are going to join these points, but using a free hand. We don't use a ruler to join these points. We join right from the start when mass was still original and time was 0. Then we are going to join using a free hand. So the initial was 200. Then we come and join using a free hand. Like that. So you see that this is my curve. It's making a graph. It's making a curve. it is spontaneously disintegrating with time. It was original 200 grams. Then as time moves, the mass reduces spontaneously, continuously. It is now becoming asymptotic when it is about to reach the time axis. In other words, it is not touching the time axis, but it is becoming a little bit asymptotic to that. Now, after you drawing that curve, what is remaining is to determine half-life. Half-life. That means we shall get the T a half. T a half here, or half-life, T a half. We can get it from the formula m naught over 2 Phi position. We can get it from this formula that T a half is m naught over 2 Phi position. In other words, m naught is mass original divided by 2 because we are halving the original mass. Remember, it is the time taken for a radioactive sample to decay half its original mass. So if the original mass is 200, then its half is what we want. So we shall now say T a half equals or is found to be at around 200 Phi position. So you see that 200 divided by 2, T a half is found at 100 Phi position, 100 Phi grams position. This is not the answer, but it's just going to help us to determine where we can find the half-life. So T a half can only be found when the mass of that radioactive sample is 100 grams because the original mass was 200. Half of 100 of 200 is 100. So we are just going now to use our graph here. We come where there is 100 here, 100 is here, and this is where we are going to put, this is m naught over 2. M naught over 2 is 100, which we've got. Then you use a ruler and you draw a line to come and touch your curve like that. The moment it touches your curve, you now draw another line from the point of connection here up to the time axis like this. You can even use a dotted line like that. Then at this point, this is where we find T a half. Now, you use your graph to read this time here. But remember, this time is in days. So you come and say, this means that half-life T a half is equal to, now this is 10 already. We have 10, but we have some small divisions here. So these smaller divisions, you can use a calculator. You use your graph, then you multiply these small divisions by the equivalent of what is in one small division. So I used an interval of 5, 5 after 2 small squares according to my square board. So that means from here up here, that is 2.5, 7.5, that is 10. Then when you reach here, it will be 12.5, but we've not reached that point. So I'm going to take 11.5. My T a half equals to 11.5. Then you can actually approximate this and say T a half is approximately 12 days. These are days. So the half-life is 12 days. That means it took 12 days for this radioactive sample to decay half its original mass. Half-life, the spontaneous disintegration of a heavy unstable nucleus to form a stable nucleus accompanied by release of energy. So the half-life from my graph is 12 days. However, you can use your graph and you get something either similar to this or slightly different when you use a graph book. Now, another part C of the question, they want us to explain the best way of storing this rare mineral. Now, much as this mineral is precious, my friend, it is very ideal to store it in a very safe place. It is actually even hazardous to human life. It is dangerous to human life since we've already noted that it is radioactive. So we have to take keen control over it. It is very, very dangerous to human life, so it needs to be kept properly. Now, they want us to give ways on how we can keep these radioactive items. So, one way, we can put this mineral, or you say store the mineral in lead containers. Why do we use lead? Lead absorbs all the radiations, the alpha, gamma, and beta. They cannot penetrate, unlike the beta and the alpha, which can be stopped by a paper and the aluminium, a smaller sheet of aluminium. So for this lead, it stops everything. That means if we keep this mineral in the lead container, it will protect it from endangering the surrounding, thus keeping it safe for the public. Another one, you can minimize exposure, to the radioactive mineral, minimize exposure to the reactive mineral. So in this case, if there is need for you to interact with this mineral, please avoid it. If you want, maybe if there is really need to expose it, if there is a rise of a need, then keep the exposure time as short as possible, because they can harm you, as we are going to see in other parts. Also, we can use store in well-ventilated rooms. So let us store this mineral in a well-ventilated room to avoid free aeration, the exchange of gases in and out, such that this mineral can not be that much dangerous to human life. Also, we can install monitoring gears. We can monitor it, but this monitoring needs, when someone is so strict, you monitor it with a lot of care. For someone who is going to monitor it, then that someone should put on lead gowns or gloves. You have to be with protective gears to protect you from these harming radiations. So, monitor the radioactive samples, monitor the radioactive material or sample with protective gears. In this, you can put e.g. lead gowns. Make sure everything that you interact with should be made of lead, such that it absorbs any stray radiations, those that can go in different directions, and they may end up endangering your life. Then part C of the question, we have that what are the dangers of exposing this mineral to the public? They want us to give dangers of exposing this rare mineral to the public. So we have seen that it is very crucial to keep the following, or to store it very safely and away from reach of people. Why? They want us to give the dangers of this. One, so we have dangers of radiations, or dangers of radioactive materials, dangers of radiation is. So I can say dangers of radiation is because these radioactive materials, they produce radiation. So they have much dangers. One, they have both long-term and short-term effects. However, in this point, you can just randomly give. They have not told you to give the short-term or long-term effects or dangers of these radiations, but you can just now give any. So we have this causes skin burn. Skin burn. If these radiations are exposed to your skin, they can cause skin burn. Okay, because they have high penetrating power. So when they penetrate into your body, they damage the skin tissues and they cause skin burn. Also, they causes gene mutation. Causes gene mutation. Now, there are high chances when you keep exposure time high, you have made your body susceptible to gene changes or to gene mutations. Your body genes can end up mutating. So you keep exposure time as short and brief as possible. Another danger is that can damage eyesight. When they are directed into your eyes, these radiations can end up damaging your eyes. Among others, we have quite a number of dangers of these radiations. For now, let us close this. Find more videos on our Metro Online channel. Subscribe. Thank you.